3, 4, 5. Oh, hi. I am Arnab Chakraborty from Indian Statistical Institute, and this is a lecture on Bayesian computations. Just now I was trying to find out the probability of head of this coin. Now I tossed it 5 times. Strange to tell, I got 5 heads. I got head each time. Now my textbook formula says that probability of head, the estimate of that will be x by n. If I get x heads out of n tosses, p hat will be x by n. So in my case, it is a 5 by 5, that is 1. What does that mean? That means that it is a Cholet coin. If I keep on tossing it again and again, I will always get head. But this does not look like a Cholet coin to me. I can see that there is both a head and a tail, and that is somewhat strange. My prior belief with coins made by Indian Mint leads me to believe that typically probability of head of a coin should be close to 0.5. However, my data, that is 5 heads out of 5 tosses, seems to imply that the probability of head should be 1. Somehow I need to balance between the two. The question is, how do I do it? Now this is something that we have to face in our everyday life. There is something which is unknown, about which we have some prior experience, and we have some fresh data about the same thing. And we want to come to a conclusion, we want to come to an estimate that balances both these pieces of information, both my prior experience and the fresh data that I have. And that is precisely what Bayesian computation is all about. Let us first get the idea using a non-mathematical example. Say for example, here I have a picture, a spoiled picture. It looks like the picture of a young man. Unfortunately, one of the glasses has been scratched out, and my aim is to restore the picture as best as I can. So that is my data, and I have my prior experience about how a typical human face looks like, how glasses looks like, and things like that. Here is my first attempt towards the restoration. This does not look like a very good restoration to me, because you see, I know that glasses typically are symmetric. This one violates that prior information. One glass is small and the other glass is large, not a very good restoration. Now here is another way of trying to restore it. This is also not very good, because it violates the data itself. Here for example, I can see that this glass looks like a square frame, but even that glass has changed to a circular frame. So it does not violate my prior experience that glasses are typically symmetric, but it does violate the data itself. So even this one is not a particularly good restoration. However, here is a third one that sort of balances things nicely. Here I can see that glasses are really symmetric, and it also coincides with whatever we can see in part of our data. So in this case, mere common sense was enough to restore a balance between what we already know and what we are seeing now. Of course, in a more general situation, we cannot merely rely on common sense, then we have to proceed in a systematic way, and that is precisely what Bayesian computation is all about. So now let us take a somewhat deeper example where we are going to use some mathematics. Again we take an example of a picture. So pretend that this is a rare picture from antiquity. We can see some yellow color. Now suppose I ask you, why is it yellow? The answer is very simple, because the painter, whoever painted it, used yellow color. So it was yellow when it was painted, so it is yellow now that we see it. Unfortunately, art historians differ. They say that during the period when this painting was made, yellow pigment was not that common. In fact, a type of orange pigment was much more commonly used, and that orange pigment has the bad reputation of sometimes fading into this present yellow color. So, how do I know if the yellow that I am seeing now was originally yellow, or maybe it was some type of orange that has eventually faded into this yellow? In order to answer such a question, we of course need additional information. For example, what is the chance that the orange will fade into yellow? What is the chance that a painter is more likely to use the orange color instead of the yellow color? It is here that the art historian has to go to a chemist. Chemists will typically sample various pigments from old paintings, and based on that they will provide precise answers to all these questions. In our toy example, suppose we get these answers from the chemist. That typically out of yellow and orange, about 20% of the paintings during that period used that yellow pigment. So, yellow was not that popular, only 20% of the cases used yellow, while the remaining 80% used that orange color. Now, we need some idea of knowing how likely are these two colors to degrade. Suppose it is known by analyzing the chemical properties of the different pigments that the orange color will fade into yellow about 50% of the time, but the yellow color is very resistant to degradation. So, if it was yellow at that time, it will continue to remain yellow even today. So, I get a diagram like this, and from this we want to know whether the original color was yellow or the original color was orange. The technique that we are going to use is very important, but turns out to be particularly simple. Just look at the diagram. Here we can see that there are two paths leading to what we are seeing now. We are seeing this now, and there are two paths to it. One is the yellow path, the upper path, and there is an orange path, the lower part. Just let us find out the probability of each of the paths. For example, the probability of the yellow path, how do you find it out? Very easy, just take all the probabilities along the different arrows in that path, 0.2 times 1, multiply them. So, the probability of the yellow path is 0.2. Similarly, the probability of the orange path is 0.8 times 0.5, that gives you 0.4. So, I have two paths. The top path has probability 0.2 and the bottom path has probability 0.4. So, the chance that we arrive at what we are observing now, we call it the total probability, that turns out to be 0.2 plus 0.4, and that is 0.6. Now, I want to find out what is the probability that it actually was yellow. We typically call it the conditional probability. This is given in a very simple way. The probability that it was yellow, given that it is yellow now, is simply probability of the yellow path divided by this total probability, which is this 0.2 divided by 0.6, which is 1/3. Similarly, the probability that it was orange is the remaining probability, the lower path divided by the total probability, 0.4 divided by 0.6, that is 2/3. So, that is the Bayesian answer to our question. Observe that this technique really did not tell us that the painter used yellow color or the painter used orange color. That is impossible to say. However, it gave us two probabilities. What is the chance that the painter actually used yellow versus what is the chance that he actually used orange? And this probability was arrived at by optimally combining two pieces of information. The prior information, that is 0.2 and 0.8, as well as the data, namely the picture as we see it now. So, now let us learn a few terms that we will be using in the rest of this lecture. First, in that example, we were trying to guess the original color, we were trying to estimate the original color. Whatever we try to estimate, that unknown quantity is typically called the parameter. Now, we of course did not know which color was used, but we knew the color has to be either yellow or orange. So, these are all the possible values that the parameter can take. Our interest lies in knowing which of these values exactly was the true value, but the set of all values that is known to us, it is called the parameter space. In our example, it was the set yellow, orange. We have some idea, the prior experience, that it is more likely to be orange or less likely to be orange. In our case, we knew about 20% of the pictures used yellow, remaining 80% used orange. That is called the prior distribution. Notice that it is a probability distribution on the parameter space. The numbers add up to 1 and they are all non-negative numbers. Of course, the most important thing in any statistical enterprise is the data. We must have data. The data in this case was the color that we are seeing now, that is yellow in our case. So, based on the information that we get from the prior distribution and the data, we create the new information to be used in future, that is called the posterior distribution, that is that 1/3 and 2/3 that we computed just now. So, these are the key terms that we will be using again and again in our lecture. So, you can see that Bayesian computation is like a box, it is like a machine in which you feed the prior distribution and you feed the data, and out comes the posterior. You can think of this as this, that prior is like the past, whatever you know from the past, and data is what you know at present. You want to combine these two in order to produce posterior, that is the information that I will hand down to the future. So, that is the main idea of any Bayesian computation. Now, of course, we do not want to make our life complicated. So, naturally, we want to stick to simple type of data and simple type of priors. Unfortunately, even if your prior is simple, your data comes from a very simple distribution, it often turns out that the posterior is not simple. It is sometimes rather complicated, and that is why Bayesian computation is an important topic. Say here is an example. I take my data x1 to x10 IID from normal mu 1 over tau. Of course, to a student of statistics, the normal distribution is one of the easiest possible, and I will give you prior on the parameters. Mu has a normal prior, normal 1 1, and tau has a gamma prior. Do not be frightened by all these numbers 2.1 and 2.5, they are not at all important. The important thing is that we are working with some very standard simple distribution, normal and gamma. But even in this case, see how complicated the posterior is. It is a very hairy complicated expression with a very complicated thing in the numerator and the integral, a double integral of that hairy stuff in the denominator. It is really scary. This slide is meant to scare you, but I hope it does not scare you away. So, please continue listening while I explain how I arrived at this complicated stuff. Getting this formula is not at all difficult. This is how I have done it. You see, there are three things that are on the screen. I have my normal distribution, I have my normal prior, and I have my gamma prior. Each one of them contributes one component to the numerator. This part, that is the part that I am showing in green, comes from the normal 1 1 distribution. You will quickly recognize that this is nothing but the density of normal 1 1 distribution. Similarly, that red part comes from the gamma prior. This is nothing but the density of the gamma distribution. I am not considering the constant parts here because they will anyway get cancelled with the denominator. And you can similarly guess that the middle part, the blue part, actually comes from that normal distribution. So, there are 10 IID normal mu 1 by tau and their density gives rise to this. And I need that complicated integral in the denominator simply to keep the total integral equal to 1. So, the main lesson to be taken from this slide is that even if you have simple data and simple prior, the posterior can be horribly complicated. So, the question is, how can we make life simple? Is there some particular choice of data and some particular choice of prior for which life will not be this complicated? Well, there are some people who have spent a lot of time on that and come up with an idea called conjugate priors. Conjugate priors are nicely behaved priors, in the sense, if your prior is a conjugate prior, it is a family of priors which is simple, then the posterior will also come from that same simple family, and that makes life simple sometimes. Unfortunately, it is not a very useful thing in practice, because number one, there are situations where they do not exist. It is not that you always get conjugate priors ready made. In some cases they exist, in some cases they do not exist. And then there is another problem, and that problem is even more serious. Prior distributions were supposed to model your personal prior experience. It is quite possible that the experience that you have does not belong to that conjugate prior type. In that case, you cannot use them. So, conjugate priors, while they do solve the problem in a mathematical way, but practically they are pretty useless. So, for that we need something more efficient. Okay, now, we are going to learn that new technique that will be useful. It is called simulation. Now, simulation is a technique that has applications far beyond Bayesian computations. In order to understand the role of simulation in the context of Bayesian computation, we have to first think of that posterior density as a surface. So, you can see that this is a surface sitting over this red flat plane, which is the parameter space, and this surface actually gives you that complicated formula. You can see that here is a peak somewhere here, and then it falls off more or less in all the directions in an asymmetric way in the form of a low lying plane. Now, when we say we want to simulate from this distribution, this means we are trying to pick up random points from that parameter space, which is that red flat rectangle that you see over here. So, the points are going to look like something like this, lots of random points. I will keep on generating more and more and more points. So, all these points actually come from that underlying parameter space. You can see that near the center there is actually more points, and near the periphery there are less points. To understand how it actually connects with the surface that you see here, I will use a little bit of color coding. You can see I have put a little orange color near the peak, and you can also see that there are a lot more points near the orange region than in the low lying green region. So, when this surface picks up, there are a lot more points over there, and when the surface falls off, there are less and less number of points. That is what I mean by simulating from the posterior. So, all these points are random, but I have more chance of getting a point when the surface picks up and less chance of getting a point when the surface gradually falls off. Now, we are going to learn later exactly how we get these points, but let us first convince ourselves that if we can get these points, what is the main advantage. So, we will see the role of simulation using a much simpler example here. Suppose that this is a dart board on which you can throw darts, and you are going to throw dart on it. Now, I will give you one region, one subset of this dart board, which is a circle. I want to find out what is the chance that the dart will land on the red circle. Now, let us pretend I am a perfectly novice at throwing darts. So, my dart can land anywhere in that green square. Then what is the chance that it will land in the red circle? You can quite easily compute that by simply considering the total area of the green square and the total area of the red circle and dividing one by the other. Okay, we can of course very easily compute that probability in this example as follows. We will first compute the area of the green square, and also compute the area of the red circle and divide the area of the circle by the area of the square, that gives you the chance that a randomly thrown dart will hit the red circle. Now, that is of course perfectly fine. However, I will show you how to do the same thing using simulation. In case of simulation, we actually throw the darts. Of course, we do not throw it manually, we will use a computer to do that. So, I am throwing lots of darts on it, each black dot represents where a dart hits the board. And then I will actually count how many of them has landed on the red circle. So, I will actually throw a large number of darts and count what is the proportion of darts that has landed on the red circle, and that directly will give me an idea about the probability of hitting the red circle. So, it is a very straightforward way without doing any computation at all. Now, let us see in our case how it performs as compared to the theoretical result. Here I have just now carried out the experiment. I have thrown 10,000 darts. So, there are 10,000 tiny little dots, out of which I have counted, of course using a computer, 7858 of them have landed inside the circle. So, I am estimating the probability of hitting the circle as 0.7858. If I do the computation theoretically, that is dividing the area of the circle by the area of the square, then I will get, you can do the computation yourself, you will very easily get pi by 4, and that is 0.7854. So, merely by throwing darts without doing any mathematics whatsoever, I could come up with a pretty good estimate, 0.7858 as opposed to 0.7854, correct up to the first 3 decimal places. That is not a bad performance. Now, simulation is very powerful in the sense it works even if that red region is of a more complicated nature. Say for example, I give you a region like this. If I now ask you to find out the probability of hitting that somewhat irregular shape, it will be pretty difficult for you to work it out using area divided by area formula. In order to find the area of that red region, you will notice that you have to carry out a twofold integration, which is pretty complicated. But the dart throwing technique remains as simple as before. I will again throw a large number of darts, suppose 10,000 of them, and just count how many lands there. In my case, I can see that 2996 darts out of 10,000 have landed in that region. So, the probability of hitting that irregularly shaped red region is estimated to be 0.2996. It is quite difficult to come up with a similarly accurate thing using exact integration. So, that is the main idea of simulation. Now, we want to see exactly how to use this idea in case of Bayesian computation. How can we simulate from the complicated posterior distributions? Well, that is the main theme of the next part of our lecture. So, stay tuned for that.